we have myself, Tom Brower. I've been acting as the HMS team lead for about a year now, coming on a year. So we're actually all rotating through. Greg went first last year, and then I've been rotating through this year, and then I think Mike's next up. So Mike's got to get ready to go for that here soon, because I'll be signing out of that role. But I've also been kind of working, especially more lately, in the lead developer role, so leading the software. So yep, Mike, if you don't know Mike, Mike's our modeling pro. He knows just about all of the software at HEC, and he's also the team lead for SSP. We have Greg Karlovitz. He's our statistical expert. Any big statistical study in the core, Greg usually gets called in. And then we have Matt Fleming, who's our division chief. And I got to say, all of these guys are modeling pros, so I don't want to give that qualification to anyone and not anyone else. This is the expert panel of modelers, and they have great things to show. And it might look like they're on going 2 times, but it's actually just them at 1x. So you might have to go back and replay this video at 0.5x to kind of follow what they're doing. Kidding aside, they're just fast. So anyhow, that's the team that'll be presenting today. Let me advance the slide. Getting used to this Teams integration here. All right, there we go. So here's the overview. We're going to talk a little bit about some of the software development practices that we've implemented on the HMS team and what that means for you, the end user. We'll talk some about how our documentation's changed a little bit and where you can find the latest and greatest how-tos and tutorials. And then Mike's going to run through a delineation. He's going to delineate a watershed all the way through to a calibrated model in pretty short order. Then Greg's going to pick up that model and show the new precip frequency grid options and hypothetical storm options we have in HMS. And then I'll do a short demo of our new standard reporting feature. And then I'll show just a sneak preview of some of our upcoming GIS features. These are 4.7 pre-release features. And then we'll talk just a little bit about some of our other upcoming features. All right, so first, software development practices. I don't know if the users are too aware of these software terms, but in the software industry, CI/CD is something that's thrown around, and that means continuous integration, continuous delivery. And this is just a diagram of our workflow on the HMS team with CI/CD. Now, the major innovation, the major piece here is that this compiling, building, and testing the code has now been automated. And you'll see in a few slides, something that used to take, weeks of time is now an order of magnitude less, something down to 20 minutes. So the workflow here is that the developer is over developing away, and when their feature is ready to go, they commit it. That commit will be pushed to a central repository. So that's where we have a whole team of developers, and there might be 3 or 4 people committing to this repo. When that commit happens, it triggers a build on our build server. So like I said, there's a script that runs through and automates all of this. When I say a script, that's a simplification, but more or less a script, a few scripts, and this is all automated. And within about 5 minutes, we have a build package ready to go with HMS. And within about 20 minutes, that build package is tested against all of our benchmarks, about 3,000 tests. And so if all goes well, we have that build package ready to go. And that build package is then made available for internal testing. So this diagram over here is our internal tester. In practice, this is often just us. I might play this role and then jump right over this role. Or maybe Matt or Mike are doing a big study. And so they pick up the latest build from the build server to start, kind of user testing it. So it goes through some internal testing. You can see these feedback loops. So if there's errors found at this level, it's coming back. If the build process, compile, build, test process uncovers some errors, it's coming right back to the developer to fix. So we're reducing the time between development and when the error is found. And so if all goes well at the testing level, what we're doing is we're trying to get the new features and the code contributions out to the users as pretty quickly. So you're seeing we have an ongoing beta program where we're pumping out beta releases as things are fixed. And then once the beta is out in the field for a while, we're calling it a release version. And this is kind of our stable version. And then we move on to the next cycle of developing features and betas. This is just an explanation. So we just looked at the CI/CD piece. This is kind of how we manage the project. So agile project management. And the traditional waterfall approach, which is how HEC-HMS has been managed for the recent history, we would define the version up front. We would define what features belong to the version up front. So it would say, this is 4.6, and this is everything that it's going to contain. And we're not going to release until we get everything done. And so in the new paradigm, we don't really attach features to a release. We say, this is all the things we want to do. And whenever each little thing is ready to go, we're going to release. So that's why you've been seeing more releases recently, but smaller releases. So the idea being, if we get a certain feature done, we want to get it out to you guys. And so we have the code in a tested deployable state at every step. So this is just little features along the way. We might define them, build them, release them, define them, build them, release them, rather than defining them all up front and going through this long process. So this is, I call it the ground truthing slide. We did all of this work over the course of the previous year and a little bit prior. And so the ground truthing is saying, okay, you did all this work. Now show me how it stacks up. So our compile build process used to take hours, if not days, and that is down to 5 minutes to compile and build, all automated on server. We didn't have a great history. We had validation tests, didn't have a great unit test. Unit test is software best practices now, and we've been applying unit tests. Those usually run in order of minutes. We have our entire validation suite, which used to take days to weeks to run, now running in 20 minutes. Our internal bug find, fix, build, test cycle is went from days to weeks to minute to hours, and that's just really limited by the speed at which we can figure out the bug. There's no other limiting factor there. And then when external bugs come in, those used to be tied up in those big release cycles, and now we're able to fix those and get releases either through our beta or through patch fixes out to the field. So we've been turning bug fixes around in our betas pretty quickly. And then, so yeah, there's the patch fix. We used to do those sparingly. We still probably will do them sparingly, but if there's anything glaring broken in a big release, we want to go ahead and put a patch fix release out that fixes that. And then our major release used to be on about a year to a year plus. It was kind of growing the time between releases. And now we're trying to get those out on the order of months. And once again, really at the speed at which we can develop and deliver those new features. All right, so here's just an overview of some of our releases since 4.4. And I put some features in there, obviously not all of them. If you wanted to see all of them, you could visit the release notes, but this is just kind of the high notes of each release. So in mid-April, release 4.4, after about a year and a half since the previous release, that added GIS delineation, which Mike's going to show you today. We also added subbasin level snowmelt parameters, which I know is big in Northwest Division. Layered green and amps losses, you might find that helpful. Computing to point from the global editors, very helpful for calibration. And then 4.4, we quickly, after we pushed a big load of features out to the field, then in came the bugs. So we did a 4.4.1 about a month later with all the bug fixes and some minor enhancements. Then 4.5, we did the global snowmelt editor. So 4.4 did parameterization at the subbasin level. Then in 4.5, we gave you global editors to edit those globally. We also added a time variable wet melt rate option. And then in version 4.6, Greg's going to highlight that today. Depth area analysis with no Atlas 14 grid was added, and we added this new standard reporting feature, which writes an HTML report, which I'll show you. And then we have 4.7, which is upcoming. We're hoping before the end of the fiscal year to get that out, and that's going to be potentially a big one. We'll see what's ready to go. Discretization and subbasin statistics should be pretty good. The expression calculator we're going to show you and 2D flow, we'll see where those come. Those are pretty big efforts.
So documentation. So this is a new direction that the HMS team is exploring. So if you've noticed, all of the documentation for HMS is now on the web. So we're not putting new content into Word files and then converting those Word files to PDFs. Instead, we're editing the content on a web application. And then the nice thing about this is once we make those edits and then hit publish, then the public can see those edits. So we have a real-time option for getting those new features documented, or if somebody reports back to us, and this has happened in the past where either the documentation wasn't clear, or it could, or just typos, or it just flat out wrong, then now we can update that documentation in a much more timely manner. So that's great. If you've gone to the website and seen the documentation, you also have seen that we have some new content. That's tutorials and guides. And so what these tutorials are supposed to be are kind of lightweight examples of how to use certain features in the software. And so if you want to know how to apply the new GIS tools, there's a nice guide in there, and some of the other capabilities too. Also, the tutorials and guides, they'll have HMS projects associated with the page. So if you want to download the project and then step through it as you read through the guide, you can do that too. So we have that. As hopefully you know too, we have our course materials from prospect classes posted to the HEC website. So if you're interested in kind of downloading those, going through them, you can have access to them. We try to update the material as soon as possible. So as soon as a class has finished, we'll get the updated material to the website. And then finally, the other thing to mention, we have the web page, a discourse page that you all have access to. And then the reason why we're migrating our support, our help, over to discourse is, so in the past, we usually got email questions. And so we'd answer those email questions, but that would just be a one-way dialogue, or a dialogue between just two people. And so the general community doesn't have access to that knowledge. And so the nice thing about discourse is the question can still be asked, and then it can be answered either by somebody at HEC or from the field. And then any person that goes to this discourse page can find that thread, that information, and then if it helps them on their project, then great. So just be aware also that the discourse content is public facing. So try to keep the content there appropriate for a public facing page. All right.
So I'm going to demo going from nothing to a calibrated model. Will not go as fast as humanly possible. So if you do have questions along the way, please ask me to explain them. But I will step through it pretty quick so you can get to some of the stuff that Greg's going to do. So first things first, I'm going to open up HMS. I'm using 4.6 beta. You can get that from our website. I'm using that because it's the latest and greatest, and it's about to be released coming up soon. So I'm going to start a new project, and I'm going to call that project Punks because we're working in the Punxsutawney Watershed. I want to place that project right here, and I'm going to switch over to US customary units. Then when I create, get a brand new project. Next step, I want to create a basin model. This will contain all the elements, subbasins, routing reaches, reservoirs, everything else that I want to do a whole lot of computations upon. I'm just going to call that one Punks 2. Next step, I want to create a terrain data instance. So I'm going to be using the NED 10 meter data set for the Punxsutawney watershed or Punxsutawney area. So I'm going to call that NED 10 meter. Now I have to actually define where that data is located. And that file is right here. I actually have a set of files. So what I started with was a base geotiff of that area. Then I projected to the Albers equal area conic projection. And then I converted the vertical units to feet. So I select that one. I'm going to set my vertical units to feet as well. When I click finish, now I have a terrain data instance that I can link to my basin model. So now I have my basin model open. I'm going to go ahead and hit the drop down for terrain data, select NED 10 meter. And when I save, now it's going to say, all right, you do not have a projection or coordinate system defined for your basin model. You got to do that. You can either select it manually, or you can just import from the GIS data source that you just used. Because my terrain data was georeferenced, I want to use that, so I'm just going to click skip. And now it imports and has my terrain data ready to go. Next couple of steps are going to be access to the GIS menu. First, I can always review my coordinate system in here, but that's all good. I want to go ahead and I want to pre-process my sinks. So this is going to create a hydrologically corrected DEM, so it gets rid of all those pits. Oh, also notice that by default, my pointer gives me tooltips, right? So I get my XY position. If I want to, let me turn off what I just got. If I select my terrain data set, my tooltip then shifts to elevations, right? So I can go to low elevations near the outlet, higher elevations near the watershed divide, good to go. But what I just created was hydrologically corrected DEM. I found all these sinks, and then I removed them and created this terrain that is hydrologically corrected. So there's only one outlet point at the outlet itself. So I'm going to go ahead and turn that one off. I'm going to go back to GIS, and I'm going to pre-process drainage. And this is going to go through my flow direction step and my flow accumulation step. You'll see that finish in a matter of seconds. Does anybody have any idea how long it'll take in ArcGIS to complete? If you're used to using that, that would be hours sometimes for large watersheds. This is about 150 square miles, so that was pretty quick. Let me go through all this stuff. I created 2 new rasters. One with my flow direction grid. Zoom in and you get a really cool picture. If I look at my flow accumulation raster, now I look at my actual dendritic watershed, right? So I see all my individual streams coming down my mountainsides and my minor tributaries going into major tributaries, going into main stem rivers, so on and so forth. Also, my tooltip has now changed, right? So on my flow accumulation raster, if I zoom in on this location, this is along the watershed divide, where I have ones, that's essentially 0 areas draining to that point, except for that cell. As I move it throughout, I get different numbers, and that indicates the number of cells that are actually draining to that location. As I get over a stream, notice I have 488,093 cells that are actually draining to that location. So that would be a location that has a whole lot of area draining to it. Let me go ahead and go back to GIS, and now I want to identify streams. So this threshold, you can redefine after the fact. By default, it's going to be based upon the terrain data that you actually used in the first place, but I'm going to go ahead and I'm going to set this to 20 square miles. So at this point, what I'm saying is if I have 20 square miles draining to any specific location, I'm going to go ahead and I'm going to call that a stream. If I turn off my flow accumulation raster in the terrain data set, now I'm left with a raster of streams. So you can see that there's a main stem that goes through here, but I also have a branch that splits off on this point, and it continues on upstream, and I have a tributary here and a tributary there. If I go back, I'm going to turn on my terrain data set again so I can see where I'm looking. Go back to the GIS menu, and I go back, and now I need to identify a breakpoint. So I want to go to my watershed outlet, and I have an actual USGS gauge that's located right here. So I'm going to go and click on the actual stream. So notice that I'm right over top of the actual stream itself, and I'm going to make a breakpoint. I'm going to call it outlet. And now when I click GIS delineate elements, I'm confronted with a manager that asks me to, if I want to, I can prefix or add a string to prefixes for subbasins. I like to call those S underscore. For reach, I like R underscore. I do like junctions. So I'm gonna, I can have the option of not inserting junctions where there are multiple elements coming together, but I do like them. So I'm gonna insert junctions and I'm gonna prefix them with J underscore. And I also wanna convert all my breakpoints to computation points. So at outlet, I'm gonna then create an element that is a computation point. And when I click delineate, now we'll be confronted with a discretized watershed. So notice that I had that tributary coming off here. That was where I had 20 square miles draining to that point. I had another split here and a tributary on the north side and tributary on the east side. Now I have 5 subbasins, 2 routing reaches, and 2 junctions that were created out of that point. Also, I have a sink that's on the downstream side. I want to turn off my breakpoints layer, so I'm not confronted with that anymore. I don't want to have these 3 subbasins right here. I essentially want to end up with 3 throughout the entire modeling domain. So I'm going to select these 2 that are coincident, go to GIS, I want to merge those elements together. And I'm going to do it one more time, merge those 2 subbasins together. Now I'm left with 1 subbasin. I have 2 routing reaches in between here. This is a legitimate setup if you have some sort of a major change in channel shape or slope or some other property within your channel. I don't. I just want to merge those 2 together. I'll select both my routing reaches, go to GIS, and I can also merge those guys. Notice that I got rid of the junction that was there as well. So one thing that I like to do at this point, I want to lock my element location so I don't drag these guys away. They're in place. And I want to start renaming things. So this guy is actually called Stump Creek. So I'm going to rename that one to Stump CK. This one is East Branch Mahoning Creek. So I'm going to rename that one to EB Mahoning. Creek. And I want this one to be named Mahoning Creek. This junction, I'm going to rename that one to, say, Confluence. Can be any old name. R_3 should be better named, so I'm going to call that Mahoning Creek R10. And then this guy, instead of Sync 1, let's just call it Outlet. Now I actually have my model discretized, named. Now I just need to start adding parameters to it and choosing my specific processes. In the Tools Program Settings Defaults tab, you get to choose all of the processes that you want to use by default when you create something new within an HMS project. As such, I have initial and constant, Clarkian hydrograph, and recession set for my loss, transform, and base flow methods respectively. I don't want to use them in this case. I want to change them all. I can click on this element and then hit the drop-down menu and change it here. It's so much faster for me to go to parameters, loss, change method, yes, and then set to deficit and constant. And now I just changed every single one of my sub-basin elements to use that. I want to do the same thing for base flow. Instead of recession, I'd like to use linear reservoir. And also for transform, instead of Clark, I want to use Mod Clark. Now I have everything set for my sub-basin elements. The process is chosen, I should say. I want to do the same thing for my routing reach, just because I constantly am forgetting to do that. I want to go to my routing method. I'm going to change that to Muskingum. I can do better than lag. I can add an attenuation on that. I'm going to give it some parameters. So the travel time from the confluence junction to the outlet location is about 5 hours. So that would be a reasonable place to start for my K value. Muskingum X, I'm going to use a value halfway in between 0 attenuation and maximum attenuation as defined by the Muskingum routing method. I'm eventually going to use a time step of 1 hour. So that would signify that I need to use 5 sub-breaches to adequately discretize this in space. Now I'm going to go ahead and I'm going to add parameters for the methods that I just chose for my subbasins. Let's first go to canopy before I forget that. I don't want to use the none method for the canopy. I want to use the simple canopy method. And this allows me to actually extract water from all of my elements, right? So I can use evapotranspiration processes to pull out infiltrated water and allow me to get a little bit of deficit. So those values, I want to use 0 for the initial storage, something really small for max storage. This is fine for those methods. I want to change this to simple for the uptake method. And now I can actually pull out water for all these guys that were actually infiltrated. I'll go back to parameters and go to deficit and constant loss. And now I'm just going to give initial values of 2 inches for the initial deficit and 8 for the maximum storage, the max deficit. I can manually just click those values in there, or I can highlight the cells that I want, right click, hit fill, and repeat down. So you can see where that would get really, really beneficial for huge modeling domains where I have a lot of elements. Now you can quickly define what you want within the global editors. I want to do the same thing for linear reservoir base flow. I want to have 2 layers for each, and I want to use the discharge per area instead of the absolute value. I don't want anything coming out of the first layer. I want 1 CFS per square mile coming out of the second layer. I want it evenly split, so this groundwater fraction says however much was infiltrated, this is how much of that infiltrated water I want you to go, or I want to go to groundwater 1. Groundwater 2, I'm also going to do 50%, so half and half goes to either one. These values should be 30 hours. This is usually based upon physically measurable characteristics as well. I like to relate them to my unihydrograph parameters if I'm using unihydrograph theory. So 30 and 200 is a decent place to start for those guys. And now I come to my transform. As we all know, Mod Clark uses a gridded representation of the watershed to define travel times and come up with a time area histogram. I can create that grid cell file within HEC-HMS now, and we all have Tommy to thank for that one. So check out how fast I can do this. First, I want to define what my projection is in the cell size, and then I'm just going to be confronted with an entry field saying, this is where I want this file to go. By default, it's going to go into the regions directory with a name that's equivalent to the basin model. I click finish, and now I actually created a grid cell file that's placed in the grid region, or placed in that regions directory. This will be the last version that you have to do this grid region step, but for now, you got to create a grid region. I'm going to call it SHG. Now I need to define where that file is actually located, that grid cell file, and that was within my data directory, or my regions directory. So punks.mod, that's the thing that I just created. I'm going to select that. I'm going to finish that. And now I have a grid regions object that's defined by this .mod file that I just created. I want to set that for my basin model, so use the default grid region of SHG that I just created, but I also want to do that in my transform for each one of those. So I open up my global editor, On the transform tab, I want to select SHG for the grid region, and I also want to give time of concentration and watershed storage coefficients. So I actually did the approach to figure out reasonable values of times of concentration and watershed storage coefficient for all these guys. Those are based upon physically measurable characteristics and commonly regression equations or tier 55. So if you have questions about that, we can talk later. I'm gonna go ahead and hit apply. Now I have a parameterized watershed. Now I just need to start adding things to it that I want to have on top, like observed data and meteorologic boundary conditions. Speaking of which, I want to go through and I want to add a discharge gauge for this location where there's a USGS gauge. Let's just call it USGS for now. It can be something that's a bit more descriptive later. Now I need to actually define where that information is coming from. So here I'm going to digress, and I want to show you where this data should be located because we talk about it quite frequently anymore. I'm in my base directory, my watershed or my HMS project directory. I want to create a new data folder. So this is something that I can manually throw data into. I can reference it, but it's all local within the project. So if I zip up this entire project and I give it to somebody else, there will be no external references to DSS files. Everything's going to work just fine when I open it up on a new machine. Everything would be hunky-dory. Just please put all your data within here. I'm going to copy and paste not only my observed time series of discharge, but also precipitation grids and temperature grids to use at a later time as well. So I'm going to go ahead and I'm going to define that location. Now I'm going to use a single record DSS file for this time series gauge, and I want to choose where that file is actually located. I just placed it right here. So I'm going to go ahead, I'm going to select that DSS file, and I'm going to click this button to pull up a selector for the actual A, B, C, D, E, and F part conventions that I want to use. So I'm going to select that guy, set the path name, and now it's all set for my discharge gauge. If I click on outlet, go back to options, and then I hit USGS for my observed flow time series. Now I can do that. When I compute, I'll be able to have a time series of observed discharge at that location. I also want to create a precipitation grid. Since we got this from the MRMS dataset, I'm going to call it MRMS. I also have a temperature grid that I want to use. I want to call that RTMA for real-time mesoscale analysis. That was the data source there. I'm going to go and I'm going to define those guys. RTMA for temperature is in the temp DSS file. I'm going to select the A, B, C, D, E, and F part conventions for that guy. Same thing for MRMS. It's in precip. And there are the conventions for the precip grid. I want to create a MET model. I'm going to just call this September 2018. That's the time period that I'm specifically interested in. Now I'm going to define the methods that I want to use. I don't want to use specified hyetograph. I want to use gridded precip. And I also want to use gridded Hammond evapotranspiration. And instead of aborting the compute if I find something missing, let's go ahead and set that to default so I can just go over top of it. And I want to choose the subbasins of interest or the basin model of interest to include those. For gridded precip on that node, I just need to select the grid that I actually defined for precipitation. I have one, so that's MRMS. Same thing for gridded Hammond, needs a temperature time series. I'm going to select RTMA. This default coefficient of 0.0065, that's a good place to start. You can play with that later if you have any questions, hit me up. Last thing, I'm going to create a control spec. And again, I'm going to call this September 2018 because that's the time period in which I'm interested. Now I'm going to go Seer 1 September 2018, start at 0000 and end at the end of the month, 0000. And I want to use a 1 hour time step. And now I should have everything all set. Let's create a simulation run. I'm going to call that September 2018. And now I'm going to choose the basin model that I actually have, the MET model, and the control specifications. Now when I save and I click compute, now I actually get a completed simulation. So I can look at the results. I can click on an element. I like to click on this button up here so it actually plots all this stuff up here. I can also go to the results tab and expand out simulation runs. Now I'm confronted with all the elements and I have a whole bunch of different things that I can look at. So if I'm interested in moisture deficit, I can do that as well. But the thing that I'm really looking for is the results at observed data locations, right? So if I pull this up, now I'm actually comparing against what was observed on the ground. So at the USGS gauge location, I'm looking pretty good. If I throw this over here, look at this guy, I can actually pull up summary statistics as well. Let me recompute one time to get those working. Now I have a Nash cycle efficiency of approximately 0.95. That's pretty good. Percent bias, I'm a little bit low on volume. and that is pretty good as well. RMSE, over standard deviation, that's also very good. If you have questions on any of those statistics and what is good, what is acceptable, we can point you in the right direction. One thing that I did forget to mention, when I started with this NED 10 meter data set, this was raw out of the NED. So I went to the USGS clearinghouse, grabbed it from here, clipped to my watershed boundary, buffered by a little bit, obviously, and then started in this process. What I could have done instead was actually go through the process in GeoHMS of burning streams and building walls. Those are two features that we don't have yet within the GIS menu. You will be able to do them in the future, but if you have a very complicated watershed or you needed to do something really weird or you wanted to define where your delineation should happen, those are two steps that you can do before you actually start in HMS. So I would actually export that grid from ARC, and then I would reference that when I create this terrain data set in HMS, and I would get what you were expecting to get for that delineation process. So that went from nothing to a calibrated model in maybe 10 minutes. Does anybody have any questions? All right, if not, I'll kick it over to Greg.
Hey, Mike, is Mike, can you hear me?
I did, yeah.
Is there a DEM file size limit?
So I've tested really big files, so like 3 to 5 gigabytes in size. You pay for it, obviously handling that amount of data takes a little bit of time for sure, but don't throw 50 gigabytes at this. Please don't do that. If you do find a limitation, please let us know. I've had people that were like, I tried 20 and it didn't quite work. So, you know, it's a decent place to start. Hydrologic modeling doesn't really require super fine scale resolution DEMs to start with. I would try and keep your DEM less than a gigabyte in size, just for performance sake. But if you do run into anything, definitely let me know.
Hey, Mike, can you show the number of cores option real quick?
Oh yeah, for sure. So if you go to Tools, Program Settings, and Defaults again, now we have this drop-down menu for number of cores. So this will be filled with a listing of the available cores, including your hyperthreads, if you do have that on your machine. So I have 12 cores available for processing. Get into the age-old description or, well, debate of whether or not it's more efficient to distribute processes across more cores or just keep your processes a little bit more streamlined and one after the other finishes. 4 cores is a pretty decent place for me to start. That allows this GIS processing to go super quick. I can start with 1 and go from there if I want, but you do have the option of defining the number of cores to use. Cool.
Thanks.
No more questions. I'll give it over to Greg.
All right, I will share my screen right away here. Hopefully y'all can hear me. I'm going to talk a little bit about doing some modeling with Atlas 14 grid straight in HMS. So we've got a new feature now that allows you to drive simulations basically based on off-the-shelf Atlas 14 ASCII grids, which is pretty nice. So if you go and you get these things straight from Atlas 14, you'll find that they come in this just generic ASCII file format. They're those familiar, friendly, giant plain text raster formats that you're kind of familiar with, but those are available for most of the country depending on the volume. And what we're now able to do with a spatially referenced model like the one that Mike just put together here is I can actually create a grid. There's a new type in here called precipitation frequency grids, and I can create a new one. I'm just going to use the 100-year 24-hour, kind of the first one a lot of people reach for. And when I create that, I now have a new option for a data source. This is only for precipitation frequency grids, but there is now an ASCII option for the data source. And so what I can do is if I go to my project now and I pull up the model that I'm working in, just the Punxsutawney model, I can grab this ASCII file. And one of the things that I do have to do on this is because the ASCII file doesn't contain any metadata in it, is I have to specify what the units are. In this case, the units of the grid are in inches, but NOAA Atlas 14 stores them with a scale factor. What that means is they stored basically floating point data as integers by multiplying by some number. That meant they could drop decimal places. And for Atlas 14, as far as I've seen, all of the cases are 1,000. The reason that we left this in here as an option, there's kind of two of them. One of them is that NOAA Atlas 2, which is still used in some parts of the country where Atlas 14 doesn't have coverage. They use a scale factor generally of 100,000. I don't know why, but they did. And then if you're ever doing a project where perhaps you have an Atlas or you have a precipitation frequency grid that's not from Atlas 14, and it might still be in floating point, you can always just use a scale factor of 1. So it's important to be able to specify that. What's cool about this then is you can now start to pull this into your meteorologic model. So what we're going to do is we're going to create a new MET model, and we're going to make it 100-year, 24-hour. It's going to be specific for this type of storm event. And when you go into the MET model, you're going to want to choose the hypothetical storm option for precipitation method. The hypothetical storm has gotten a lot of love recently. It's a pretty powerful tool for doing a lot of sort of design-based modeling or risk-type modeling. And so we're going to continue to enhance it, mostly because it's got a pretty powerful breadth of uses that we can kind of turn it loose on. And I'm going to make sure that I include that basin model in there too when I get that going. So you're going to be kind of confronted with, if you haven't used this before, with kind of an unfamiliar set of basically tools in here. And what we're going to do is we're going to work with the user specified pattern type of storm here. And what this is just how is the rainfall distributed in time. The hypothetical storm largely replaced what was just the SCS storm patterns in the past. We started by adding some area dependent patterns, which are for one of our specific development partners, but it does have some power for other types of hypothetical modeling. But we're going to work with a single user specified pattern, and we'll define that one in a second. We're working with a 24-hour storm right now. And one of the things that we do want to do is we want to switch the precipitation method within the hypothetical storm then to precipitation frequency grid. And what that's going to do is it's going to give me the option to now specify the grid that I put in there. And what's cool about this, and I'm going to pull up QGIS real quick here, is so this is our watershed. I exported these from the GIS menu after doing a delineation. So these are straight from the model. And this is the Atlas 14 grid underneath it. It looks like there's a pretty neat little gradient in here, but what's really kind of funny is the volume of Atlas 14 that I'm working in right now actually covered a gigantic area. And HMS right now has taken in this entire raster. The color codes look kind of funny because I basically set the color scale based on this display extent so we can actually see anything. But the values that are actually in this extent are all pretty flat. There's not a lot of mountain terrain kind of going on here that really change how the dynamics of the extreme precipitation happen. But I did want to show you that there are different values here. And so when we start to do some averaging, we'll actually see some changes happen. So what's great about this is you don't have to sit down. You don't have to clip out Atlas 14 for your subbasins. You don't have to do any zonal statistics. You're working with this native raster straight from Atlas 14 that HMS will automatically do all the spatial processing for you on. So in order to actually define the storm, we do need to get a pattern in here. And so what I'm going to do is I'm going to create a new paired data of type percentage curves. So there's a few ones in here that have the name percentage or something that might make a lot of sense. And so we're going to try to winnow those down in the future. But the one you want for a time pattern is the percentage curves. And what I'm going to do is I'm going to put a code in here that I'll explain in a second. This is a second quartile, 10th percentile storm. And the reason I call it that is if you go to the Atlas 14 webpage, there are these temporal distributions. They correspond to an analysis that was done for each of the volumes of the Atlas. And it basically gives you a CSV. I did not want Excel, I want a notepad. A CSV that's full of these non-dimensionalized storm patterns. What's great about these is they give you a ton of tools for coming up with time patterns for basically hypothetical storm modeling. They break them down into 5 cases: first, second, third, and fourth quartile, which are basically which percentile of the storm has the most rainfall. And then they did an analysis of all storms that occurred in the area. And so this doesn't really care where the peak intensity was. And then it also quantifies those by basically how extreme of a first quartile storm is this. Is a huge amount of the rainfall happening in that first 25%, or is it just barely 25% of that rainfall? So this basically gives you the worst case scenario, a 10th percentile, whereas something that's a larger one is going to be a little more mild. So what we're going to do is I defined one for the second quartile, 10th percentile storm, and that'll be this one here. What I've actually been doing is I've been pulling a lot of these into a DSS file just for using later because I got tired of importing these things by hand. But what I did is I highlighted here all of the percentile storms for second quartile. This is for the Ohio River Basin and surrounding states study area, so the same map that we were looking at before. And when you plot them up, this gives you an idea of what these curves actually look like. There's basically a percent of the total storm duration, percent of total storm volume. The 10th percentile is this worst one right here on the left, 90th percentile on the right. So we're going to use this kind of steep one here on the left. And to do that, now that I've got this paired data defined in HMS, and I called it second quartile 10%, I'm actually going to link it to a DSS file. I'm going to go to my data folder where I've already copied this general patterns DSS file. And then I'm going to choose the path that has my second quartile 10th percentile storm. And after I save, we can plot the graph. We can verify that's the one that we wanted. And now when I go back to the MET model, what I can do is specify that storm pattern. So now I've got a time pattern, I've got a spatial pattern, and now I'm going to specify an area reduction and a computation point. So what this all does in conjunction is from a computation point that you select, so you have to set a computation point in your model. What it will do is it will take the area average of this Atlas 14 grid above that drainage area. So in this case, it's the entire watershed. It takes the area average. Now, bearing in mind that Atlas 14 is a point precipitation product, what you have to do in order to get to an average is you have to apply area reduction. Otherwise, you're going to over apply rainfall. It's going to be just way too high. So you have to apply an area reduction. I'm using the default of TP40. I would recommend for site-specific studies and anything that's not 24 hours in duration, especially, to use the user-specified option and develop your own area reduction. And so this is automatically going to compute that area average, reduce it, and then it's also going to distribute it in time according to the storm pattern that we created. So I'm going to get this thing running by creating just a little 72-hour control spec just to make sure the whole storm gets routed through the watershed here. And I will edit this just to give it some rational starting and ending times. Of course, if I was typing well, that would help. All right, I'll create a new simulation run here. I'm not going to be too descriptive. Well, we'll give it a better description than that. We can always do better than that. 24-hour, 100-year outlet. And I'm going to choose the basin model that we have, that 100-year 24-hour MET model that we created, and that 72-hour control specification. And then when I go to run it, it'll zip on through because it's a pretty short simulation. And there we get a result, which is pretty nice. And then when we look at the results, what we can see for that run when we go to the outlet is this is the application of that area average rainfall reduced and then scaled using that second quartile 10 percentile storm. Well, that's all fine and good. And a lot of these kinds of studies where we're applying this, we're really curious about flood frequency at a number of locations in the watershed. And one of the tools in HMS that really gives us a lot of power to do these analyses quickly is the depth area analysis. And what that does is it automatically, for a number of computation points, repeats this process. And so what I'm going to show real fast here is how to set one of those up. So for a depth area analysis, in this case, we're just going to say this is a 100-year, 24-hour. And notice I'm not going to even worry about location because we'll see that in a second. Same basin model, same MET model. So I didn't have to change anything, which is really nice. Here, I'm going to set the same period that I want to run as I did with the control spec before. And I think in the future, the simulation will want to look like this too. Now, there's a tab over here, analysis points. What this does is this actually replaces the computation point that we had originally set up in the hypothetical storm. So it's going to ignore this completely. In fact, you could set it to none if you use this as a depth area analysis. It doesn't really care. But when you go here to the actual depth area analysis, imagine I want to know the 100-year flow for all of these subwatersheds. I'm going to say I want to know it for Stump Creek. Imagine maybe I've got a little culvert coming out of there that I want to size. East Branch Mahoning Creek, same little deal. I want to know what happens when I get to the combined flow. So I have the confluence. Maybe I want to know what it looks like just for the local flows below it. So that's Mahoning Creek is that lower watershed. And then the whole kit and caboodle down here at the outlet. And so what this will do is this will automatically do the area averaging for each of these computation points. So it'll take the Atlas 14 grid, we'll say the first analysis point. It'll take the Atlas 14 grid, get the area average just for Stump Creek right here. And then it'll use the area reduction factor for the corresponding area above. And then it'll distribute it with that time pattern. Then it'll go to East Branch Mahoning Creek, repeat that process. Then for the confluence, it'll get this whole area above, repeat that process. From Honing Creek, it'll just run the local one. And then for the outlet, it'll run the whole watershed. So let's get that running here real fast. It'll zip right on through, 5 iterations, 5 analysis points. And what's really useful is here in the console, you can kind of check your work a little bit, because each of the iterations or any run of this hypothetical storm will spit some useful information out. One of them is what the hypothetical storm depth was, which would be your area average. That's unreduced. It tells you what the storm area was, and in this case, it's telling us basically that we're assuming that the storm area is equal to the drainage area. That's kind of a shortcut we take when we're doing these kinds of models. It might not be realistic to assume that a storm, if we're going to model this watershed, the storm is going to be a perfect 157.3 square mile storm with this exact shape. In real life, they have very different patterns, but again, these are fairly idealized, mostly just to aid in some of these design procedures. And then it also tells us what the area reduced hypothetical storm depth is. So you can see here that the effect of looking up 157 square miles on the TP40 chart is going to reduce a 5.4 inch average down to about 4.96. And if you go up in the console, you can see that for each of the iterations right here, these values are a little different. So for an 87 square mile one, it reduced its average from 5.4 to 5.05. Now, what's funny is these values don't vary much, and that's not an accident. It's because when we look at this grid and we think about it globally, if I were to set this puppy up so that you can see what's going on in space, you're going to realize that basically it's flat as can be here. So this isn't a super exciting area to see the difference happen. And so most of the magic is happening by applying a reduction factor that's caused by varying the storm area. But in areas where it's highly dynamic, the spatial variability of that point precip frequency can be very high. And so automatically accounting for that by changing up the modeling using the depth area analysis is really powerful. So that's a demo, though, that combination of features.
Okay, good deal. Yeah, let's we'll come back around. We can stay on for questions. I'll just show you really quickly our new reporting feature. This is a 4.6 feature as well. It's pretty cool. Tools reports menu from HMS. You can print out this HTML report. And there's some options. Hey.
You need to start sharing.
Sharing. Okay. I think I'm sharing. I don't know. Teams is throwing me for a loop here.
I can see your screen.
Okay. Okay, maybe it's selective sharing. Sorry, Greg. But for those that can see, I have this nice, pretty HTML report pulled up, and you can do summaries for like a global summary, similar to our global editors, and then you can do summaries for both parameters and results at the element level. And you can see here's just like an outflow. So a nice reporting feature. You might find that useful in some of your submittals. Let's take a look real quick into the future. This is 4.7. Mike said that .mod files and grid regions are going away. .mod files will kind of hang around. The notion of grid regions, we're starting to phase that out. This is what we're calling a discretization. And you can see we have discretized this Punxsutawney subbasin or basin. This is 1,000 meter grid cells. The cool thing that I can do is change that discretization if I want. So I'm just going to select 2,000 and I'm going to recompute those grid cells. And what it'll do is change the grid cell size, and maybe computationally, for whatever reason, you might want to optimize the grid cell sizes. So the cool thing that this opens up is just the opportunity to pretty quickly change the grid cell sizes and use different grid cell sizes throughout. So you can see there 2 different grid cell sizes. The other cool thing that's coming in the near future, Josh from Fort Worth has helped us out doing some of these sub-basin statistics. I'll just pull it up. Well, there I have one basin selected. So let me unselect that and show you the statistics, parameter statistics, sub-basin. So there we have statistics for all of the basins. So that's pretty cool. Longest flow path, centroidal flow path, some slopes, relief, a lot of statistics. If there's a statistic we don't have and you want it, just let us know. But what that's going to do is going to play into our new expression calculator. So I'll just show that off real quick. I have deficit and constant losses real quick, and this looks very similar to global editors you're familiar with. But the new thing, you can see where we're going, is we've added this expression calculator, and we're going to allow users to start like doing calculations based on those statistics. Some of the fields, you can do calculations based on fields in the table. And you can also access the grids that are in your model to do calculations based on. So that's going to be kind of the new parameter estimation addition to HMS that's coming. And then real quickly, let's talk about some of the other new stuff that's coming up. Compute speeds are going down, which is the right direction for compute speeds. Let's see, 4.4 to 4.5 to 4.6, each level of the way. We parallelized in 4.4, and then in 4.5 we did a enhancement based on accessing the paired data curves that speed that up, especially for snowmelt models. Adding global meta editors, the snow global, and we added monthly average ET. Upcoming, Mike's been working really hard and has a big team there working hard on 2D flow and sediment. So that should be coming. That's the screen capture you see in the top right. And then cumulative flow for reservoir sediment, or sorry, cumulative flow. That's the plot you see here on the bottom right. You can see we have this new cumulative flow output. And then we have a reservoir sedimentation feature coming. And then for those of you who like the Mac platform, we just did a Mac OS build, which is kind of cool. And then I think that is all I have. Let me just